Okay, so this is going to be our last video for this unit on differential equations. So we're going to start with slope fields. Slope fields are little tangent lines drawn at points to a function where the equation of the tangent line is given to you. Okay? So here they give us this equation. This equation only depends on x. So for instance, when x is 3, the slopes would be 2. Slopes of 2 look approximately like this, right? When x is 2, these slopes would be 1. When x is 1, these slopes would be 0. When x is 0, these slopes would be -1. No one's going to be measuring the slopes exactly, but they should look symmetrical to the positive ones. Right, then these would be positive 2s. Right, -2s, you know what I mean. Then at negative 2, these would be -3s. You get the idea? And then -4s. Okay, so that is a slope field. Now, if you look at number 2, all of these depend on y. So when they depended on x, they were all the same vertically. Okay, so slopes equal vertically. So these slopes are going to be equal horizontally. Okay? So, all right, let's say we start with y is 0. Well, if y is 0, these are all going to be 0. Okay, let's do y is 2 and -2. If y is 2, these are all going to be 1. And then if it's -2, these are all going to be -1. And then these would be a half. And these would be -1/2. Okay? So that's how you organize them. I wouldn't make a chart or anything for a problem where you just have x or y. I would just do it. Now, when you have x minus y, you might want to make a little chart. Okay, you might want to organize these by x values. So you might have x remain constant and then y vary. Okay, so I'm going to have x equal -3. But you could see that there's going to be 5 points. Then I'm going to have x equal -2. Then I will have x equal -1, 0. Then I'm going to have x equaling 1, 2, and 3. Okay, so then we get y. All right, so we're just going to substitute in y. We'll start with +2. And we'll go down to -2. Okay, so then I'm going to get the slopes for each of these. So I'm going to sub in and get the slopes. Okay, you can pause it and do those on your own. Okay, so check that your slopes are the same. And then you're just going to graph these slopes. All right. So I would start with the slopes that are 0. So if you look at the slopes that are 0, right, I have -2, -2. Okay, then I have -1, -1. I have 0, 0. Okay, I have 1, 1, 2, 2. Okay, I just realized this should have been 2 here. Sorry about that. Okay, so then I'm going to keep in mind, what is this line? This is the line y equals x. So if you realized from the beginning that when y equals x, those slopes are 0, you could do that. Okay, so now I'm going to do the slopes of +1. Okay, so I have 3, 2. Okay, I have 2, 1. Okay, you could see the pattern here. Once you start to see the pattern, it becomes easy. All right, so then I'm going to look at the slopes of 2. So I have 3, 1. So just make that a little steeper. Then I have 2, 0. Get the idea? Okay, so I'm doing these in groupings. Okay, so then I'm looking for the slopes of 3. So I have 3, 0. So I'm just making this a little more steep. Then I'm looking for the slopes of 4. And then I'm looking for the slopes of 5. Okay, so then you go on the other side and you're looking at, I'm looking at the point. All right, I'll start with 1, 2. So that slope is -1. So I'm just going to try to make it match the 1, but be on the other side. All right, so now I'm doing all slopes of -1. So I have 0, 1. I think you could see the pattern here. Then I need all slopes of -2. Okay, so for instance, I have 0, 2. Okay, then I need -3. Get the idea? Once you figure out the pattern, then it becomes easy. -4, -5. All right, so that's how you do slope fields. All right, I'm going to post this worksheet. Okay, you'll be doing these slope fields in class, numbers 1 through 6. That will be our flipped work, the beginning of the flipped work. All right, now let's look at other types of problems. So here they're saying to match the slope fields with their differential equations. Okay, so first let's start off with the easiest one, which is dy dx equals x, right? So this means for each x value, the slopes are the same vertically, right? So you can see that that would be choice B. Then let's look where the y values are the same. Okay, and that would be here. So horizontally, they would be the same. That would be A. Okay, that helps you to eliminate 2. And then we just literally did the graph of question 8, so we know that's D. And then these are the same, okay, for number 7, these are the same going vertically. They're all the same vertically. It's sine of x. Now, think about it. What function has a derivative of sine of x, right? So if you have dy equals sine x dx, and you separate these variables, y is going to equal negative cosine x plus or minus a constant. So if you think about the negative cosine curve, so think about positive cosine, right? So positive cosine starts at 1, then it goes to 0, right? You know how the curve looks. So now if you flip this over, okay, you should be able to see that if you went through 0, 0, okay, you would see that you have these curves. So the little tangent lines are, these slopes are the tangent lines. So when you look at these slopes, if you take those values and graph them, they make the graph of sine of x, because that is the derivative of negative cosine x. Okay, but all these curves are negative cosine curves shifted up and down. Okay, so in class, you're going to do the next matching column, and you can analyze number 15 in class as well. That could lead to a good discussion. I'm not going to do that one now. Okay, so this question number 16, all right, you want to know which of the following could be a specific solution to this differential equation. So I don't know if you can see this clearly, all right, but number one, these all rely on x, so that doesn't help us. Okay, it's not sine or cosine. You could see it's not cyclic that way. You could also see that we don't have lins through this function. So we narrowed it down between C and D. Well, if you get the derivative of D, we get 1/2 x, right, squared. So if you look at that compared to this derivative, y prime is 2x, right? We can compare the two of them. So if you had 2x at 0, either way, these would both be 0, right? But the difference is this squared means that all the slopes will be positive. Do you see that all the slopes are positive? That's why the answer would have to be D. Okay, I'm going to take a look at number 17 with you, and then I'll have you try number 18 in class. So number 1, you're going to make these slopes. So xy divided by 2. Okay, when either x or y is equal to 0, these slopes are 0, so you can get that done. Then go around in a pattern. So let's say we try 1, 1. That would be a half, right? If we tried negative 1, 1, that would be negative a half. If we tried negative 1, negative 1, that would be positive a half again. Then this would be negative a half again. Okay, so do them in a pattern, like going out, like an explosion, exploding out, okay? Then if you try 1, 2, the slope's going to be 1, negative 1. Okay, I don't have those on the graph on the bottom. All right, so then what if you try 2, 1? Those slopes are also going to be 1, right? Negative 1, positive 1, negative 1. And then you just have these last few to do. Okay, so you can substitute those in and try them. And they're not looking for perfection. No one has the time to sit there and be so picky, okay? They're just going to look for the pattern and see that they match up. So in the next question, we want to write an equation for the tangent line through the point 1, 1, right? Well, I already know the slope at 1, 1 is 1 times 1 divided by 2, or a half. So my tangent line is y equals m times x minus x, 1 plus y1. All right. Now, if I substitute in 1.2, right, I'm going to get y equals 1/2 0.2 plus 1, which is 1.1. Okay, in part C, it says find the particular solution. So if I separate the variables, I have dy over y, and I have x over 2 dx. Now I'm going to integrate this, so I get ln absolute value y, x squared over 4 plus c. So I'm going to exponentiate both sides. I get absolute value y equals e to the c e to the x squared over 4. And then I'm going to name this plus or minus e to the c to get rid of the absolute value. And then I'm just going to call that a. So I have y equals a e to the x squared over 4, sorry. And I'm going to put in my initial condition 1, 1. So I get 1 equals a e, that's a 4, to the 1/4. Okay, which means that a is 1 over e to the 1/4. Okay, or you could say a is e to the negative 1/4, either or. So now I go back and put this in here into my general solution. So I have y equals e to the negative 0.25 times e to the x squared over 4. Now I can combine these, so I have x squared over 4 minus 1 over 4, right? So that's just e to the x squared minus 1 over 4. And then we're going to find an approximation for 1.2. So f of 1.2 is approximately e to the 1.44 minus 1 over 4. Okay, now we want to know whether or not this approximation from part B is an over or underestimate, so you get the second derivative to study concavity. So for the second derivative, I have to get the derivative of the first derivative, right? Well, I have my first derivative. Here it is. So I'm going to use the product rule. So first I'm going to write this as 1/2 xy. Okay? Now, constants factor out of derivatives, so I'm just going to leave the half outside. Okay, so I have the derivative of the first times the second plus, then I have the first times the derivative of the second. But remember, I already know that dy dx, okay, is equal to xy over 2. Okay, so I have to think about concavity. Okay, so if I think about the concavity at 1.2 e to the 0.11, that's what that simplifies to, 1.2 e to the 0.11. If I substitute this in, then I'm going to get that I don't need the value, I just need to know that the second derivative is greater than 0. So since it's concave up, okay, the approximation in B is an under approximation. All right, and then this other question next class. Thanks.